Comets are the universe's messy artists. They fly in, get warmed up, and start shedding gas and dust, so sunlight and the solar wind can sculpt these long, elegant tails that almost always point away from the sun. That's the basic rule. So when you see a comet-looking object with a feature that seems to point toward the sun, your brain does the perfectly normal human thing. It lights up the "wait, what?" sign. Now, before we get dramatic, let's ground ourselves in what we're actually looking at. This image was captured on December 13th, 2025 by Tirasak Thalorng in Rayong, Thailand. The overlay here tells you the essentials. It's 271 exposures of 30 seconds each, totaling about 2.26 hours. The telescope is a 0.26 meter f.4.2 reflector, and the pixel scale is about 1.43 arc seconds per pixel. So we're not talking about a random blurry snapshot. We're looking at a serious, stacked observation designed to pull out faint structure. And there's a crucial little label on the left, Sol 293 Deg, with an arrow. That's the direction of the sun in this frame. Keep that arrow in your mind like a compass needle, because the whole controversy lives and dies by that geometry. Let's also talk distance, because distance is the difference between wild mystery and normal physics doing normal things. NASA's own overview of 3I ATLS says the object stays far from Earth, with a closest approach around 1.8 astronomical units, about 270 million kilometers, or about 170 million miles. That's not close in the everyday sense, but it is close enough that we can track the object well and compare imagery across many dates. Wikipedia's compiled orbital solution gives the closest Earth distance on December 19, 2025, as about 1.797 AU. So we're in the same ballpark, around 270 million kilometers. And yes, at that distance, what you see is delayed by light travel time, roughly 15 minutes. That's true, but it's also not a magic trick. A 15-minute delay doesn't create a sunward tail. It's just a reminder that astronomy is always looking into the past. The photons are ancient messengers, and we're the nosy neighbors reading their mail. So what's the weird part? Here, you see a bright central condensation, the nucleus region plus inner coma, and then a faint extension that seems to be oriented sunward in the direction of that Sol arrow. People online often call this an anti-tail or a sunward jet, and the claim goes like this. Gas and dust should be blown away from the sun by radiation pressure and the solar wind, so a sunward-directed feature shouldn't persist. That claim contains a real physical intuition, but it also glosses over something important. Comets can absolutely produce sunward-looking structures without breaking physics. There are at least 3 big, boring, powerful explanations that can each create sunward-looking features, and the key scientific question is which one dominates here. Explanation number 1 is the classic, the anti-tail illusion. Many comets show an anti-tail when Earth's viewing angle makes dust in the comet's orbital plane line up behind the nucleus in our line of sight. In other words, it can look like a spike or tail points toward the sun, even though the dust is still behaving normally. It's perspective, like railroad tracks converging in the distance. Nothing supernatural required. If that's all it is, then the sunward feature will be strongly tied to viewing geometry and should change as Earth, the comet, and the sun move. Explanation number 2 is that not all tails are the same. Comets have dust tails, ion tails, sometimes sodium tails, and a whole zoo of structures. Ion tails are pushed and shaped strongly by the solar wind and tend to be straighter. Dust tails are pushed by radiation pressure and often curve. Near the nucleus, inside the coma, the flow can be complicated. Jets can produce arcs, fans, and asymmetries. Some of those can point partially sunward close to the nucleus before they get turned around. Think of it as tossing confetti into a strong wind. At the moment it leaves your hand, it can be going in almost any direction, but the wind eventually wins. Explanation number 3, the one getting the most discussion for 3I ATLS, is about the lifetime of particles. Here's the punchline. If the sunward-facing material doesn't live long enough to be pushed into a long anti-sunward tail, it can appear as a sunward glow or stubby extension without ever becoming a classic tail. And that's exactly what Eric Cato and Abraham Loeb model in a paper on the ice coma of 3I ATLS. They propose that the pronounced sunward feature seen in early high-resolution imagery can be dominated by sunlight scattering off grains of water ice ejected from the nucleus, with the appearance evolving with heliocentric distance as sublimation rates and grain survival times change.
That's a very physics-first idea. It says, tiny ice grains are bright scatterers, but they're also fragile. If they get launched sunward, they can create a sunward-biased brightness enhancement near the nucleus. Then they sublimate away before radiation pressure has time to push them into a long conventional tail. So you don't get a dramatic anti-sunward dust tail from those grains. You get a localized glow. Now, the internet loves a clean narrative. NASA ignored the anomaly. But reality is messier and honestly more interesting. NASA hosted a public event on November 19, 2025 to share imagery of 3I Atlas gathered by multiple missions and telescopes. NASA also published updates through its science channels, including mission-specific observations like stereo imaging. So it's not that nobody's looking, it's that 1, the object is far, 2, the data is complex, and 3, scientists tend to be careful about what they claim until the modeling and comparisons are in. And that brings us to the phrase people keep throwing around, sunward jet. Let's be precise, because precision is how you keep wonder from turning into nonsense. A jet usually implies a collimated directional outflow from an active region on the nucleus, like a nozzle. A sunward glow or sunward coma asymmetry can be broader, not a clean beam, but a brightness enhancement. In this image, what you see is not a needle-thin laser, it's a compact extension. Calling it a jet might be accurate, or it might be overselling what the data actually resolves. The right move is to say, there is a sunward-oriented brightness feature, and we're trying to understand its cause. So why does this keep sparking debate? Because 3I Atlas is not just any comet, it's interstellar. NASA describes it as an interstellar comet passing through our solar system, staying far from Earth, reaching closest to the Sun around late October 2025 at about 1.4 AU. Interstellar objects excite scientists because they're literal samples from other star systems. They carry chemistry and structure that formed under different conditions. So when you see a morphology that seems odd, your brain understandably whispers, is this a clue to alien chemistry or just normal comet physics wearing a funny hat? And then there's the non-gravitational acceleration discussion. Many comets deviate slightly from purely gravitational trajectories because outgassing produces tiny thrust. That is normal. For 3I Atlas, some analyses of astrometric residuals argue there is evidence for a non-gravitational component over parts of its observed arc. That by itself doesn't imply anything exotic. It's basically the same reason a balloon doesn't follow a perfect ballistic arc. There are forces besides gravity acting on it. The real question is whether the magnitude and direction of any non-gravitational acceleration can be reconciled with plausible outgassing and jet geometry given what we see in the coma. So if you're watching this and thinking, okay, but how do we decide between illusion, ice grains, or a real jet? This is where science gets fun because it becomes a detective story with testable predictions. Prediction 1. Geometry. If this is mainly an anti-tail illusion caused by dust in the orbital plane, the feature should vary strongly with viewing geometry, Earth's position relative to the comet's orbital plane. You would expect the sunward look to come and go or change character as the line of sight changes. Prediction 2. Sublimation physics.
If the sunward brightness is dominated by short-lived ice grains, then the feature should be most prominent at the distances where ice grains are produced abundantly but still survive long enough inside the observing aperture to scatter light, then fade or transform as the comet moves closer and the grains sublimate too quickly, while longer-lived refractory dust takes over and produces a more conventional tail. That's basically the kind of evolution Cato and Loeb are modeling. Prediction 3, rotation and repeatability. If it's a real jet tied to a specific active region on the nucleus, you might see consistent directionality patterns linked to nucleus rotation, and the feature might repeat in a periodic way, though at this distance and brightness, detecting that cleanly is not trivial. And here's a subtle point most hype videos skip. Image processing can exaggerate structure. Stretching, filtering, and stacking can reveal faint features, but also amplify gradients and create the psychological impression of a clear jet when the underlying signal is a more diffuse asymmetry. That doesn't mean the feature is fake, it means you have to treat morphology carefully, ideally comparing raw frames, different processing pipelines, and independent observers. Now, let's address the dramatic headline, "Science wants to ignore this." Nah, science doesn't want anything. Science is a method, not a personality. What actually happens is more mundane. Scientists prioritize the explanations that require the fewest new assumptions, and they publish when they can quantify things. Meanwhile, the internet prioritizes narratives that feel like a movie trailer. Both are human, but only one reliably converges on truth. That said, here's the part I genuinely agree with in the anomaly hunting mindset. Anomalies are where discovery lives. If everyone had dismissed the first weird spectra of exoplanet atmospheres, or the odd orbit of Mercury, or the cosmic microwave background noise, we'd be poorer in knowledge. But the right attitude is, "That's weird, let's test hypotheses," not "That's weird, therefore it's definitely something wild." So where does that leave 3i Atlas today with this image? It leaves us with a beautiful, high-effort observation showing a compact coma and a sunward-oriented brightness feature, one that can be interpreted through known comet physics, but still deserves careful comparison across dates and instruments. And here's the cool part. You don't have to pick a side like this is a sports match. You can just be curious and rigorous. If you're an observer, you can contribute. Consistent imaging, calibrated processing, reporting geometry, and sharing data so others can compare. If you're a viewer, you can do the rarest thing on the internet, hold two ideas at once. This looks weird, and we might have a normal explanation until the evidence forces a decision.